All right, now that you guys can actually hear me, I'm experimenting with having both screens up so you can totally see what I'm looking at. Is it too much of a bother? Can you not really read things clearly, or is it fine? If it becomes too much of a bother, just let me know and we can change it. But my goal was to have the paper up as we're going through and building this sort of code base. So just let me know, and we can revert it back to one screen. In the meantime, let's get on to what we're doing. So all I've done here is run the, if it loads, nbdev new command. All right, I want to say it's nbdev new. Yeah, nbdev new, and all that did was convert our repo into an nbdev one. And this is mostly because I plan on making this a fastai package, fastai extension package, and I'm going to rewrite some aspects of their model just to make it a bit more friendly towards fastai. Now, I'm also going to be keeping in mind, in case if Jeremy decides that he wants to stream tonight, then I'll be doing most of this over on the fastai Discord, but for now, we're just going to roll with it here. So, spent most of today rereading over the paper and really analyzing some of what it's doing. And I guess we can start by just going over some of the notes that I have written down. Now, I annotated the paper by hand. I'm kind of old school. I don't use any online annotators or anything like that, so I just printed out the paper and just went through it. So, some key aspects with this paper is that I have written down. So we have two different forms of attention. We have self-attention and intersample attention. If you're following along with the paper, which let me go ahead and throw a link to that in the chat here. If you're following along in the paper, this is page 2, and it's the second paragraph. So we have self-attention and we have intersample attention. Now, the key difference between the two of these is self-attention is with one row, whereas intersample attention, as the name sort of implies, is between many rows. And so essentially what happens is Saint can go through, and if, say, a certain row is missing a value, it can pseudo perform with the other rows to try and make up for that one sample being missing. It's a clever approach to fill missing, because essentially you fill missing by not filling the missing. You just replace it with the other rows that are in existence. Now, a question that came up in Twitter land obviously was, well, okay, but how does this work whenever you're in production, right? Because you might run it with only one row, you might run it with many rows. And the way how you counter that is you just feed it a batch of the training data, and then you add that last row, that new row, at the very end. Eventually, we'll get down to looking into that. It's certainly something a little interesting. Now, intersample attention, the way they describe it right here, they say that intersample attention is akin to a nearest neighbor classification, where the distance metric is learned end to end rather than fixed. So we'll be looking into that over time as we go. Now, in the meantime, some other interesting bits is if we go down to the deep tabular model section, they talk about tab transformer, and usually in the realm of machine learning, when it comes to neural nets and tabular models, we've only known embedding the categorical features, because That's what we assume. They're categories. We can relate categories to one another. What they do is embed the continuous data as well. And as it says sort of here, the main issue with this model is that continuous data do not go through a self-attention block. That means any information is lost. This is talking about tab transformer. In our model, we address this issue by projecting continuous features and categorical features into a higher dimension, embedding space, and pass them both through transformer blocks. In addition, we propose a new type of attention. This right here is that intersample attention that they're talking about. Just going through my notes here to see if there was anything else of interest. Section 4, I had on a few things. So this is, section 3 is talking about their self-attention and intersample attention transformer, the model. I believe it's all the way down here. Yep. So, similar to masked language models, in the beginning of each of our inputs, we add a class token, and this is where that attention dives from. And then you can see essentially as the model goes through, each of these red dots is a multiplication, and then eventually all three of these vectors are concatenated into one before being passed. So that's mostly what I have written down when it comes to that and explaining it, which I know this is pseudo high level, but it's just some notes that I've taken. And then one thing I found very interesting was the generating augmentations section, as essentially what we have going on here is something that Sylvain Guger had sort of theorized at one point in time when it came to tabular models, and that was that you could perform cut, mix, and mix up in the latent embedding space, and that's exactly what they've done here. So they first apply mix-up, first they apply cut mix in the raw data space, the cut mix that we know from Vision. So you basically cut and paste two rows together, and you roll with that. And then after they pass the embeddings, you then also perform mix-up. And generally what this does is, it allows for better generalization, but it's a very clever way of using both cut mix and mix up. Now, the one thing that'll make it tricky when it comes to the fastai implementation is fastai likes to do stuff like this through callbacks. So, we have a mix up and a cut mix callback. Here, we don't quite have that ability because we are applying mix up directly to the model itself. In our implementation, we're going to work around that. We're still going to include a mix-up callback, but it's going to be a bit different than the mix-up that you're familiar with, if you are, because what we're going to do instead is adjust how the model takes things, more or less. Otherwise, that was basically the notes that I had taken so far on the paper and interesting bits that I had seen. So, now that we're done with that, let's go to some NBDev stuff and start exploring their code base and see what we can learn. Now here, I'm just going to essentially rewrite what they have here into NBDev, and along with that, write some documentation. And also, I want to rewrite their model as what it would look like if it were in the fastai code base. So like where modules get imported from, how the code tends to look, in situations like that. What I'm hoping that will do is give us a slightly different looking model than what they have, but it shouldn't lose any of what it's doing, if that makes sense. Essentially, we're just going to refactor their code. And then as we're going, we're going to attempt to also compare code to paper implementations in the math so that people can see the parallels between the two. So that's kind of why I wanted to record the stream with both screens, so that way we can have our code on the left and their code on the right, and we can just directly parallel between the two of them. All right, so we'll call this O1. Let's see, does the augment require any model imports? It does not, so we'll call this one O1 augment. Then we'll do a hard default export. And we'll call this augmentation. A new markdown, and we will call this tabular augmentations. Cut, mix, and mix up based on the Saint paper. All right, so if we look here, looks like there's really only 3 functions to add. Let's go through and just rewrite this first ourselves, and then we'll add some documentation along the way. So we'll do add our export tag, import torch, import numpy as np. And then our first section, this should be code. Over here is going to be masking. This is the embed data mask function. So let's look what we have here. So we have embed data mask. Now I'm going to rewrite this similar to a NBDev documentation style that Jeremy showed a while back. And what that means is we're going to document the inputs as we're going. So I'll sort of explain what I mean by this. So we'll have xcat, which should be a tensor, really a torch.tensor. We have xcont, which is also a torch.tensor. We have cat mask, torch.tensor, cont mask, and then vision dataset. All right, now before we go any further, let's document this a bit. So xcat is input categorical features, input continuous features, mask of categorical inputs, mask of continuous inputs. Now, likely as we're going, we'll switch this up and make it a bit more readable. So like, where does cont mask and cat mask and cont mask originate from? But for now, this works. And if we see essentially what we're doing here, we pass it to the embeddings and then generate some attention based on them. And so essentially what we've done here is we just pass our data through the attention layers, the input categorical and continuous. So this is that, I believe this should be parallel to the, to what I mentioned earlier with that, going back to the paper. The Ramblings of a Mad Scientist. This should be the equivalent, I want to say. No, it's not the equivalent of self-attention. Never mind, don't mind me. So let's go ahead and write out this function of ours. So device xcont.device, and then we'll say xcat. We can rewrite this a little bit, make this in place, save ourselves a little resources. Model. Oh, okay, we missed our model. So we'll do net. Should be, how do you generally describe the type of a PyTorch model? Does anyone know? Stream quality is a bit low. That's annoying. Let's see if I can't fix some of that a little bit. Also, sorry about that, Dr. HB. It's hard to see the code and hard to hear as well. Okay. All right. So in that case, we are going to change things a little bit. We're going to increase that. B, let's get rid of that display. And then we're going to adjust this. That wasn't quite what I wanted to do. All right, so minor technical difficulties. All right, so we'll go ahead and only capture one screen. And the last thing we need to do is how did I do that? Bear with me for just a moment. That's how we did that. Output, video. All right, we're going to temporarily hide everything, and hopefully this will help us do that. Okay, ideally we are back to the world of the living, and everyone can see me okay. Let me know if we can't for whatever reason. Well, we can't see me. That's annoying. Why can we not see me? That's because that went off screen. Also, sorry about that, guys. I was hoping that we could be clever here, but apparently not. All right, well, I guess we'll have to go without seeing my face for a bit. Sorry about that. That wasn't quite what I was hoping to have us do. But I don't think I can manage to fix that right away. Let's see if I can do... Yeah, no. Okay. So we're just gonna have to go without seeing me. But that's okay. I'll just switch the monitors that we are currently doing things on. All right. So we have this back. Can we all see me okay? As I work towards redoing everything. All right, awesome. Sounds like that helped a lot with the quality of stuff. All right. So back to what we were doing here. So essentially we're rewriting the model architecture, right? So I'm using a beta, alpha, in process documentation design that Jeremy came up with for NBDev. Uh, he's not 100% sure if this is what it's going to be like, but it's pretty close. So basically, it's kind of written, if you're familiar with um, coding for like server or client side applications, it's sort of similar to how they like to document things. So essentially, we have our variable, the type, and then a comment with whatever its documentation is. Can I help you? Uh, Now here, so what we're going to say here, because net can be a variety of things, we're just going to say the Saint architecture. And vision dataset is the dataset, a vision dataset. This way we don't have to write things more than once. Now it's not going to show up when we do NBDev. It's not going to show up when we do NBDev show docs, and that's mostly because it's actually a true feature yet. It's something Jeremy's playing with, but I wanted to try and write with that format to see just how it is. And so far, I do like it. So I'm kind of hoping that it becomes a main place in the NBDev library. But in any case, let's get back to the task at hand. So I'm gonna rewrite this definition that I see here, uh, and let's see if hopefully this won't wind up being too small. However, I think I also have it set as a. Do I have it set as a display capture? Questions I should know as I'm streaming. Oh, good, I do. Okay. All right. So I'm going to zoom out of this because that's way too close for me. We'll zoom that a little bit. Let's rewrite this a little bit into something more towards what I would do. So we're going to do some things in place like this xcat net categories offset dot type as xcat, and then xcat encoded equals net dot embeds xcat and 1 and 2. So that's our continuous values, I assume. And then that'd be the shape of it, so that'd be batch size number. And then n3 x cat shape. So more cat. So basically n1, n2, and 3 are batch size, the number of continuous, and then the number of categorical variables. Let's go ahead and write that. N1, N2, N3. Batch size, and cont, and then if model.cont embeddings equals MLP, well, we're going to assume we only have MLP embeddings. And I'm going to go ahead and let my cat out. Because in the spirit of fastai, we just want our defaults to work, and then if there's more options, then we will deal with it there. Because essentially we have if embeddings, otherwise raise an error, so we'll just pretend that's not there. And actually this helps us with our model definition, or our function definition. embed and mask the data through the embeddings with MLP attention. So we'll get rid of this. And then xcont encoded equals torch.empty and1 and 2, and then net.dim, which is the I think that was the dimension that our continuous values needed to be. Now here we have for I in range net.n num continuous xcont encode I equals net simple MLP at I xcont. Is there a way that we can reduce that code? Any for loops we can make faster is better. And if we have a lot of continuous variables, that gets very long very quickly. Let's think on this for a moment. Let's see also, unfortunately, okay. Just keeping an eye on the Discord as well to make sure that if Jeremy starts streaming, people can watch that. There's probably a way to do this that I'm just not seeing right now. Because what is the shape of xcont encoder? Xcont encoder is n1, n2 by dim. N2 should already be the number of our continuous, should it not? Do we need this for loop? Can it be done quicker? Things to look into. All right, so in any case, we'll just keep rolling with it. And then looks like we move things to devices. Xcont encode.2 device. That's fine. And then we have cat mask temp. Mask plus model. So we have our offset here. We already did that once, didn't we? Cat mask, comp mask, categories, offset. Let's think of how we can refactor that a bit. Write a subfunction. We'll call this offset. We'll have this be net. We'll call this model atra type. We'll call this tensor type. And all we'll do here is return nested atra, which we'll need to call from fast core for that. Yeah, nested atra lets us do, you'll see in a moment, but it lets us do something like this. We can say nested atra model, what we'll do, model dot, is there a reason we're not creating an module? That's a fair point. Because it kind of is a layer in of itself, isn't it? Because we have xcat, xcont, cat mask, comp mask, model itself. We'll make a note of that down here. Can we rewrite this as a module? Because we definitely can. I do think that we can rewrite this and just have it as a layer. If we just rewrite this a bit. Very good thought. It's definitely something that we can think about and think towards because it would allow us to simplify a lot of things. So nice call. And for now, let's roll with this. So I want to do nested etra model dot. So we have categories offset, comp mask offset, mask embeds cat. That's fine, but we have a bunch of offsets. So we'll do model, then we'll say atra, and then what we tend to do underscore offset. Then we'll do model. Actually, this should be get atra. Atra. Is that right? Would make that a lot simpler. I guess we don't need to use nested atra here. So we'll just do apply offset model atra tensor type, and then we'll do get atra model atra. Oh, that's why we wanted that. Okay. Dot type as, and then we call that with our tensor type. So essentially what we do here is anytime we want to apply an offset, we pass in the model, the attribute, and then the tensor byte if we want to change to, and it lets us get rid of a few of these redundant calls. So with that, we can do xcat plus equals apply offset. And then we'll do net categories. And then xcat, and that should be the same. And then here, we can replace this with apply offset net. Here we have cat mask and do cat mask. And we'll do con mask. I think these are temporary functions. Do we have cont mask or con? Yeah, we have cont. Cont mask plus apply offset net cont mask. Cont mask. All right, that helped clean us a little bit up, make it a little more readable. Let me call this mask embeds cat and cont. That I don't think we can quite change. I wonder why the original author made the function separate from the actual net. Maybe there's a reason. I don't think there is. They like to be a little bit more explicit than things and not hide too much stuff going on in the model from what I can tell just based on what I'm seeing. So we can introduce it as a layer later on. And then we have mask temp equals net mask embeds cat mask temp. There's not really much we can do here. Cont mask temp net dot mask embeds cont mask temp. All right, and then x categorical encoders at cont mask equals 0 equals that. All right, so we'll do x cat encode at cat mask. So where cat mask equals 0, we'll set that equal to cat mask temp cat mask equals 0. There's probably a way we can reduce this code a bit more, but this will probably take 2 to 3 iterations before we truly have a condensed version. Let's const mask temp mask equals 0. All right, so this should be, so essentially we're masking any of our missing values, if I understand this correctly. This is a spot where it would be nice if we had a little function with what is going on here, but that's okay. All right, so then we just return xcat, xcat encode, and xcont encode. And up here we can do returns tuple of torch.tensor, torch.tensor, torch.tensor. And just so we can make this documented even more, again, this is just me experimenting with things. So this first tensor will be our new X category. Or new, we'll say new categorical input. New continuous input. And then our last one is, well, actually, categorical encoding. New continuous. I think that's a bit more accurate towards what's going on here. And there's the cat again. You can never pick a room. All right, so we're a little further now. We've got this first function done. Now, next we have mix up and add noise, which noise in this case is cut mix. So for the sake of simplicity and one-to-one, we'll write it as cut mix and mix up. Oh, where did you not like me there? That's where you didn't like me. Tuple expected at most one argument. Okay, maybe now you'll like me. There we go. All right. Now let's move towards actual augmentations. So we'll do cut, mix, and mix up. And this is where things get a little interesting because I'm because hypothetically this should be able to work with even our regular tabular model that fastai has based on what I'm seeing in the code and from what I understand of what's going on here. But let's first write this normally, and then after we've converted their code base over, probably not next stream, but the stream after, we can look at rewriting these how we can as fastai callbacks. So we're going to do export def mix up, and well, we'll say we're probably going to need to import fastai. We'll call this saint mix up. And yes, I'm writing a function definition as a class, but technically it's a class in fastai, so I'm not going to worry about it. All right, so we're going to do that, and then we'll say x1 is a torch tensor And then let's do one tensor in a batch, x2 torch tensor, another random tensor in a batch. Then we have lambda, which is a float. There's one. That is lambda to apply on inputs. And then y, which should be a torch tensor. Defaults to none. Targets. And then use CUDA boolean equals true, whether all right, so far I really do like this style of documentation. It very much so lets me just think about the input as I'm sitting there trying to write the function, which, you know, when we're dealing with NBDev and wanting to do these, you know, continuously without losing our train of thought, that is very nice. So I applaud Jeremy for coming up with this approach with NBDev, which obviously was inspired by a bunch of other things, but it's a really nice way to go about this. All right, so mixing up inputs and returning pair of targets. And now let's go even further with this and do our outputs, which returns a tuple of this should be a torch tensor x post mix up. We'll say mixed up x1 mixed up x2. There we go. That tells us roughly what we need to know about this. And honestly, yeah, that works. Mixing up and returns a pair of targets. I like that. Yeah, it's a lot of text, but I don't think that's necessarily bad. All right, so here we'll do batch size x1 dot size 0. We can one line that. Could say index equals to device, which we can get to device by calling from fastai dot where is it at? Fastai to device. Torch core. Torch core import to device. And how did I lose the chat? Where did you go? Where actually did you go? All right, everyone vanished from me. I would like my chat, please, stream, if you would be so kind. Thank you. All right. Now back to the task at hand. All right, so torch core to device. This should let us, probably going to give me a yelling about my GPU, but that's fine. We can ignore it. Now we can do to device. Well, actually, what we can say is device equals CPU. If not, use CUDA, else CUDA. All right, so we can do to device, torch, ran perm, batch size, device. That should roughly do the same thing I want to say. To device, torch dot ran perm, 3 CPU. Yep, okay. Just want to make sure that we actually get a tensor back, because that would be very bad if we just magically lose an index tensor. All right, and what on earth did I have on this side of the page? Probably the same paper. Oh wait, that's right. Because we had everything here. All my left side of my screen just basically vanished on me. So it's a stream. In any case, all right. So now we can do. Well, essentially, we do the same thing here. We do lambda times x1 plus 1 minus lambda times x1 index colon. So let's write this as that, and then we want this to be private, and then what we can do is apply over in torch core. All right, good, it is. Then we can do mix x1 mix x2 equals apply underscore mix. Actually, we can do partial underscore mix with lambda equals lambda, index equals index to both x1 and x2. All right, so that saves us a little bit of code, which basically all I'm doing here is rather than writing these two functions together, I make it modular and just do apply, which if we look at what apply does, it just applies recursively to a function. And to me, this is still clean enough that I understand what's going on here. But just in case, we can always add a little documentation. Applies mix to both x1 and x2 on lam and idx at index. All right, so that's documented enough. And then if y is not none, y a y b equals y index. Then we return mix x1 mix x2 y a y b. Otherwise, return mix 1 mix 2. Now that we've rewritten this, I think it would do us well to go compare how that looks to the fastai mixup callback. Because it should actually wind up looking very similar. So we have mixup, which is actually a little bit different, but the implementation should roughly still be the same. Another thing that's a little different is we have torch lerp here rather than this, but if we actually look at what torch lerp is doing, I think it's pretty close. So something to think about whenever we look towards integrating with fastai is how can we make fastai's existing... my chat went away again. Why does it keep wanting to take you away from me? I don't like that. I want to actually be able to sit here and talk with you guys. That's very annoying. All right, let me go ahead and pop out the chat again. There we go. Please stay there this time. It will be much appreciated. All right, so there's our Saint mix-up, and now let's do our cut mix. We'll call this Saint. Oh, we need an export tag. Saint cut mix. All right, so if we remember here, I mentioned that cut mix is so mix-up itself is applied on the Oh, hey Huddy. Awesome. Glad to see you joining us. That's really, really cool. Go ahead. Well, so, all right. Yep, that's terrifying. Absolutely terrifying. Everyone is here. I don't even know how many of you are here. The chat tells me nothing about who all is actually here. Oh, there we go. Ah, it's three of us. Well, at least we have some form of an audience. That way, if I mess up, only a few of you know we're here. Only mildly terrifying. All right, so now we have cut mix, which uh, when I mentioned earlier, so the difference between mix up and cut mix is mix up is done on the already embedded features, whereas cut mix is applied in the beginning. And so that's why we have xcat and xcon. So let's go ahead and rewrite this. So we'll say cat is a torch.tensor and is the one batch of categorical data. And we'll say xcont. Ah, we have 4. All right, so we have a new torch tensor, one batch. Oh man, everyone is streaming in. Did I just miss something? Oh no, everyone's coming in. Well, cool to see everyone here as we get more and more people joining our ridiculous mess that is whatever we're doing. All right, so we have one batch of continuous data. And then we have our noise params. Now here, since we only really have one kind of noise that's implemented, they have forward feature. They have this forward feature thing here, but we're going to ignore that because really the only thing implemented is cut mix. So that's why we're calling it Saint cut mix. All right, so then we'll say lambda type float 0.1 lambda to apply on inputs. And that should be it. And then we return a new torch.tensor. And we will call this newly noised X input, or we'll say newly noised categorical features. Tensor, newly noised continuous features. And then we'll say applies cut mix on tabular data. Okay, we have a model definition. I will say it's a bit longer to write these because you're thinking more about how each of the inputs are, but I don't necessarily think that's an issue for me. I don't know. I'm still playing with it. I'm still playing with it. I'm not opposed to it. It does make the code much more readable, and I mean, I don't know. You guys are the audience. You tell me if this is very readable to still have a one-liner code definition, but you have all the inputs defined here. All right, so now let's work through bringing this in. So we have device equals x cat.device. Actually, we can make that even further. We'll say batch size and device equals cat.size at 0. And we'll also do xcat.device. All right, and then idx torch.randperm batch size cat core torch.from numpy. Okay, this is a very interesting piece of code. Thanks, Ari. Have a good night. I want to rewrite this right away. I I don't know why, but I feel like there's a better way to do that that's more computationally efficient. But let's see. So what we have here is, so if we start at the inner, we have np.random. Actually, even before that, category dot shape. All right, so we think of x cont that should be of shape n by, yeah, yeah, numpy to torch. We're losing some form of efficiency here, especially with all the clones and detaches. Um, all right, so we have np random choice 2 xcad.shape. We're just going to assume is batch size by 32. It's roughly what I'm going to assume our x category is going to be. And then probability is 0 0.1, 1 minus 0 0.1. All right, so this is all that is. And then on top of that, we wrap that in a torch dot from numpy. And we also push that to a device. So if we time this on my omega slow computer, let's see what we get. 73 nanoseconds, not nanoseconds, microseconds. Um, torch random choice. Let's Google and see what we can find. Oh, interesting. So torch has no equivalent implementation of np random choice. Is that still true? Because this was 2020. Things that surprise you. And why does my chat keep vanishing on me? PyTorch. This is quite annoying. It won't let me talk to you guys. That's all I want to do. All right, there. I've got the chat up on my phone. We're just going to roll with it and pretend like nothing happened. Implement. All right, here's a torch issue. It is still open. Well, that makes me sad. We actually do not have an equivalent of NP random choice. All right, well, let's think about what this gets back with me. I think the solution would be, well, well, actually, no, there isn't really a solution. Yeah, there's a solution here, kind of, but not really. That's actually really disheartening. All right, so we have to do that. Okay, that's just what we got to do. We call that twice, and that's very annoying. So we'll call this def. Didn't we do something like this similar? Apply lambda. And we'll say I shape lambda device. And what we'll do is we'll return start from numpy np.random.choice I shape p equals lam1 minus lam dot to device. All right, and then that lets us convert that to just apply lambda to, we have what? xcat.shape. Lambda is lambda and device. All right, that cleaned it up a little bit. Cont core, apply lambda. And we have 2 xconst.shape, lambda, device. I'm not 100% sure if this actually makes it a bit more readable or simpler, because we are applying separate functions and reducing like 2 lines of code, but I don't know. This is our implementation. We can change it as we see fit later on. Also, this entire time, I've honestly thought that you could see me on my webcam. That's funny. All right, so now we grab our proper x1s. So we do x1, x2, xcat index, xcont index. That's an interesting naming convention. Do we ever use the original xcat? We do. Okay, so let me do xcat core, xcont core, xcat.clone.detach, xcat.clone.detach. Yeah, not sure if this is helpful either, but that's okay. Xcat core at cat core equals 0. x1 cat core equals 0. Xcont core all right. Well, we did clean it up a bit, but that was mostly because we got rid of some if statements and stuff. But there's our tabular cut mix. Now, do we derail and try this cut mix out on the adult sample with regular fastai? That would involve converting this over into a callback for us to use. And we go do that. This will eventually need to happen anyways. Actually, this is a pre-processing step, isn't it? Xcat, xcont. No, this would be that. Well, you guys tell me. Do you want to derail temporarily and go apply this tabular version of cut mix, which is actually pretty generalized to a certain extent, over in fastai callback form and try it on adults very quickly and derail, or sit here and converting the code base? Because we're about to go into the model. We just technically finished augmentations with that. So let me know what you guys want. Yeah, I see you looking. Pick your poison. All right, so then we'll do export hide from nbdev. Oh, how do they do it? Jeremy likes to, yes, let's see what happens. All right, let me first export this code, which all I'm doing here is Jeremy tends to, well, from what they've stated, it does tend to improve even on the adults because that's what they did. But yeah, Jeremy tends to export in the notebook. So we'll do nbdev export import notebook to script. Notebook to script. All right. There we go. Now we have the start of our little library. All right. Let's go open up a Colab notebook and try this out because I currently don't have access to a GPU. All right, I'm going to open up a Scratchpad. And let's write some callback. Change our runtime. Do pip install fastai-u. And go to one of my bookmarks. I'll throw this in the chat, which requires me to actually get to the chat. But this is usually what I use to get all of my examples. So we'll do from tabular.all import star. And we'll go down to the tabular portion. All right, so we have this. And now let's write some mix-up. All right, so I'm going to open up the augmentation here. We'll go down to our St. Cut mix. So we'll call this class tabular cut mix. And we're going to have it inherit. How do we want to do this? We'll do this based on what we have here first. And then maybe, since we're kind of derailing, go through and throw fastai's regular cut mix at it. So we'll just have an inherit callback. Also, template off of fastai cut mix, which really is templating off of mixup. Callback mixup. Just want to remember roughly how we do things. All right, so I want to copy the mix handler class here. We're not going to use it, we're just going to base off it. So we're going to have run valid equals false. This ensures that it's only done on the training data set. And then init self alpha 0.5. Now this is that lambda. Actually, it's not going to be the same thing here. Because in our instance, the distribution here is, yeah, it's going to be very different. All right. We'll store this lambda value then and just set self.lam equals lam. All right, so now we want to do, should be before batch. Yeah, before batch. And are we applying this to self y and self x? All right, so we'll call this applying cut mix on the batch. Now we're basically just going to copy paste what we had here and refactor it just a little bit. All right, so we have xcat x cont equals self.x. All right, and then that should work. batch size, x cat, cat correlation. Then we do self dot xb equals x cat core x cont core. I want to say hypothetically that's all we have to do to have this work in fastai, because actually that's a good question. Do we ever override the y's? Where's the code at that I have up? I think it's over here. Okay, so we have that. Last thing basically I want to see is how we affect the y. Okay, we do. All right. So we're looking at our version here. Mix up, add noise. Yeah, they don't affect the y's. That's very interesting. I wonder why they don't do that. Because usually when you apply cut mix, you do stuff to both the x's and the y's. I'm looking at the source code here. Let's quickly go take a look at the training loop and see why. Cut mix. Noise. Embed data mask. They're not affecting the y's here. That definitely feels like a bug. Because usually you should affect the y's when you affect the x's. So we're gonna do that in ours. Cause I mean, well, we can try it just one for one with what they're doing. But we'll make a note of that. Note. We need to affect the y's too. All right, well, hypothetically, we have it. Let's go see what bugs we have. Part of why I'm doing this madness is so you guys. No, they said it was basically done. When I talked with the author last, that it was done. They were gonna add a few doc strings, but basically that's it. It's exactly what they ran with. So let's see what we find out. We'll do data loaders, 200, 100. Actually, we already have a learn. Learn fit one. We'll do fit for what? 10 epochs, 1 in 3. Callbacks, tabular cut mix. 0.2, because I think they use 0.2 in their experiments. Let's see what we break. Because we always break something. That's just the nature of how it goes with these things. All right, we broke something. Lamb is not defined. Yes, that should be self lamb everywhere. Which actually, if it's self lamb, we don't need to pass in lambda anymore. So we can get rid of that. All right. Now let's try it. X cont core. Oh, did we miss something? think I might have missed something. Let me go pull up the code real quick. Pre-trained model, data. I have it on the other screen. That's the only reason why you can't see it. Augmentations, cut mix, add noise. Xcont core, where were you defined at? Oh. Xcont core, Xcont. What do you mean it's not defined? Oh. Missed an R. The shape of the mask 3 at index 1 does not match the shape of the index 10 series 6 2. Xcat.shape, xcont.shape. Let's go investigate and make sure that we're actually working with the right things here. 647, 643. I'm missing something. Cat, cont. Because those two should parallel. Apply lambda. All right, sounds good, Dr. HB. See you later. Probably doesn't like that we're doing this. Am I indexing that right? Index, comma. Yeah. Allegedly. That should be it. All right, let's do this the old-fashioned way. Take the code. Cat cont y equals next iter DLS at 1. And then we'll do lambda equals lamb equals 0.2. Device equals cat.device. Batch size equals cat.size at 0. In the clone, I have both cat. No. No, I have both cat and cont in the clone. Cat x cont, x core, cont cat, cat, cont, cont. Nope, that's not quite it. Let's make sure we're not missing anything in the fastai Discord, which looks like we're not. All right, let's see where we're going next. So next we do torch.randperm batch size. So all this does is reshuffle our batch into a different shape. X1, which is really cat idx, comma. Should maintain the same shape. Yep, it does. All right. We'll say what am I supposed to do with this? All right, so now we have the index. Cat.shape. And then we have our, I'll do it down here. Cont core, which is our cont.shape. That's right. X2, x cat, x cont at index. That should be right. So we have x1, x2, x cat index, boom. Cont index, boom. Which we've already shown that that's fine. All we did was shuffle. So then we do x cat core, x cont core. We have cat.clone.detach, cont.clone detach at detach. We already know what that did. All we did was clone and detach those. It's cat core cat equals 0. All right, so that's fine. All right, so now our issue is the cont core, which here gave us issues. So let's see what happens. We have x cont core equals 0 equals x2 cont core equals 0. Why did that magically work? All right, well, considering it magically worked, let's just go ahead and throw in what we did here. I might have missed something very imperative, which might relate to what you said there, Hater, but I'm not 100% sure. All right, so that's the same as that. Index, torch room, that's fine. And torch NP random choice. 2 cat cont dot shape. Self dot land minus wool. Okay, that's fine. So that should be fine. X1, X2 is X cat, X cont, index, boom. I'm just going to go ahead and do that. All right, and then I'm doing this copy paste way because what I'm hoping we'll find is where my typo is, but it doesn't. Yeah, that's what I'm looking at, but I just copy pasted the code and there was no difference. Okay, well, there it goes. Ah, yes, well, we do need to do that. Self.learn.xb to actually change it. So we'll fit once like this, and then we'll fit again without it. And we'll see if it makes some sort of difference. Now it is the adult sample data set though. That generally is very hard to get above 83, 84%. So anything we do get back, I'm not 100% sure how well we can even trust it. But we're at least toying around with cut mix applied in a tabular form. And we'll just very quickly do this. Mostly what I wanted to make sure is that we could actually run it. Because if we can successfully segment it out, then we can have it as a fastai callback. And there we go. But let's see what happens if we do this. Because a few things I'm interested in seeing is A, is there actually an increase in accuracy? And B, what's the time difference like? It looks like it's just 1 second, which isn't too bad, all things considered. Um, but let's mostly see how our accuracy does. Now, the highest we ever gotten here was 0.837, which actually seems to be a little low, depending on how we split the data. But let's see what happens. 837,531, 83793. We also ended on a slightly lower accuracy as well. But a common trend that you see is training loss is generally higher than the validation loss, which means it is working. That does mean it's working. I wonder if we can fix that. I wonder if that's because of the Ys. Is what I'm curious about. Because it is working technically, but I think it can be made better. So what do we do to self-YB? Torch slurp, wait, let's squeeze. All right, so I'm just gonna throw this to the side here, and we're just gonna throw some fastai code at it and see if it magically fixes things. All right, so let me do Y. Should be something like Y core. I think we just mimic what we do here. We do Y equals Y self dot Y index, boom. Y core equals Y self dot Y dot clone dot detach. Hypothetically, this mimics what they did before. So it might work. A lot of what I tend to do is just throw things at things and see if it works. And if it breaks, then we roll with it and figure out why. So let's see what this did. Probably gonna get something about that. Okay. If we do something like this. Does not like that. All right, let's do this as a tuple, y core, comma. It really does not like that. All right, so if we do .0 dot shape, let's try and make these as close to what they're expecting as we can. Probably should have raised an error there, but that's fine. All right, so that's fine. Another thing I don't like is the fact that we can't do tuple y core, because technically that's what it should be. Which I know is probably going to break again, but maybe we need tuple of a tuple. All right, well, I'm stumped. Where'd we go wrong? That's where we went wrong. Looking at A to B, we have tuple L. All right, so let's see how this does, which technically this is applying how we did there. That is exactly how we did on our cats, on our Ys. And the model seems to be struggling a bit more. That's not something I would expect to happen. Because normally you'd expect that you'd, adjust your X's and your Y's. But this looks like it's going to struggle all the way through. Why is that? How's our loss function here? Let's see what we can do. Let's try and mimic FastAI's mixed handler classer. So we'll do def loss function self cred might be, and I'm actually just going to straight up copy paste this. Also import from fastai.callback.mixup port reduce loss. All right, then that should be fine. The rest of it, learn.lossfunc.yint. All right, so it is stack Y. Self.oldlf, self.learn.lossfunc equals self.learn.lossfunc, self.lf. After train. So basically all I'm doing here is migrating over the mix-up code that we have in FastAI into what we have here. Or this is really cut mix, but it should be both the same thing, even for the cut mix implementation. Yeah, the cut mix implementation uses mix handler, which is where this stems from. So then after train, self.learn.lossfunc equals self.oldlf. All right. Tabular model has no self.yb1. How do we do this? So y is the original, yb1 is the new. So what we do here is just say self.yb1. And here we do have self.stackY, so we ignore that if statement. Well, we're no longer starting out in the 70s, so that's good. But we're also not very stable. Now, granted, I did not attempt to find a learning rate while we were doing this, which is something that we're taught to do. But that's fine. Maybe. It's still flatlining at around 82. So since we're not adjusting the y's, the only real conclusion I can make with this cut mix is we tend not to be. I'm just thinking from how this is going. My educated guess is this implementation of cut mix essentially relies on improving the feature selection, is my guess. Because essentially what we're doing here is throwing noise into it. Actually, isn't that what they called it? Yeah. Noise. No wonder why this is working like it is. And now this is all coming back to me. It's not a bug. It's a feature. Where was that at? I know the page, and we can talk about that real quick. Da, 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 da. Oh, eventually I will just have all of these. Eventually I'll wind up having like all of these pages scattered all across my room. But I want to get this out there for when we. There it is. Okay, so let me go ahead and pull up the page in the paper and we can sort of talk on that. I literally read this and highlighted this section, so I kind of wish that I had talked about it in the beginning. It would have made a lot more sense, but that's okay. So it's a section on how robust is Saint to data corruptions. And so essentially what they did to augment the code in that way, or augment the data set, which is really just throwing away the data set, is they did cut mix, which as it says here, replacing 10 to 90% of the features with values from other selected samples. Now it's personally, I'd say cut mix is loosely the term, because cut mix is about affecting the x's and the y's, whereas here we're just completely noisifying the data by giving it messy X's. Hey Seam. So, I'm not sure how much of this you've seen so far, but they discuss applying tech cut mix on their tabular inputs. And what the implementation reads and what I just sort of half solved of a non-issue is the fact that it's not really augmentation. It's data corruption. And so normally when you apply mix up and cut mix, you affect both the x's and the y's by some lambda. Um, but here we're just applying the x. And they do that to simulate corruption. We apply cut mix, replacing 10% to 90% of the features. The drop in the mean is very minimal up until 70% data corruption, when the performance drops significantly. So this then begs the question, does that mean it's only really using 30% of the data? Which then would correlate back to feature importance, but then that means it's just completely ignoring the rest of it. And I don't know, it feels yucky. It feels yucky to me. I don't know why. And it says Saint and Saint I. Saint I means the one with the inter-sample attention. Models are comparatively more robust than Saint S, because Saint S had a very stark decline. The showing shows that row attention improves the model robustness to noisy training as we anticipated. However, we find the opposite trend when many features are missing. Saint S and Saint are robust, and the drop in accuracy is not drastic even when 90% of the data is missing. So when you have a lot of new data with a bunch of missing features, Saint S, which should be the regular self-attention, and regular Saint with no self-attention, still managed to do quite well even with very little data. So we essentially just show that that's what it's doing. Um, yeah, we did go on a bit of a exercise tangent to sort of prove them, because as we literally saw when we affected the loss function, it failed. When it didn't, we were fine. So that's probably where I'll end the stream today. I'll go ahead and throw what we have up into the fastai repo. Along, or not the fastai repo, geez. Our little Saint repo that we have going on, our Saint fastai repo. And I'll throw this tabular cut mix class that we made that goes through and applies it. But with that, I guess thank you guys for joining me with me for the stream tonight. We didn't quite get enough done as I kind of expected. I imagine the next stream will get much more into rewriting the model architecture potentially, if not just training and working off of what we finished last week, or last week, 2 days ago, yesterday.